Try this one on for size. Really, really quickly, this first graph right here, function or not? Yes or no? Function or not? Function. Here, sorry, there's a little glitch, so I'm not sure what I'm getting at there. Here, function or not? Well, if I look, there's no single double points on the same x value function. What about here? Not a function, right? Run your vertical line along, touches right there, there, not a function. What about here? Not a function. What about here? Not a function. This is a sideways parabola. To get a graphing calculator to graph a sideways parabola is a pain. You'd be amazed if it's not a function, the hassle you have to go with to work around the software. What about this? Not a function. What about this one? I think it is, yes? No? Yes? No? Yes? No? 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 Right there, no, right? And also right there, no. So no. We'll talk about this weird one in a day or two. So circles are great examples of graphs that aren't functions. Ovals aren't functions. What does that mean? It means, Curtis, if you're wanting to graph this on a graphing calculator, you have to cheat. You have to graph the top half as one equation. You have to graph the bottom half as a separate equation on the current software that we have. So that's one reason that it's important. Any questions from the homework that you were going, I'm not sure how I can figure out which ones of these are functions or not? Okay, if you got it done, great, hand it in. If you didn't, hand it in the next couple of days. Hey, the first thing you need to do is cross out where it says lesson number 2 and call it lesson 4 part 2. I typed this, I was using somebody else's, I was cutting and pasting, and I did everything great except I forgot to change the title. Duh. I've changed it now. What we want to look at is translating graphs, because I think this is going to give us a better understanding of when we start to talk about domain and range. We're going to start off with some review. Because remember, a graph can be written as a coordinate plane, shown below. Label all, I'll add an L there later, the important points. First of all, quadrants. What quadrant is this one right here? Quadrant 2. What quadrant is this one right here? 3. What about the top right quadrant? 1 and IV or 4. Oh, then I notice it says blank axis right here. Which axis is this? X-axis. Which axis is this one down here? The y-axis. And what do I call that there point there in the middle? Begin the letter O. Do you remember? The origin. So some good quick terminology. It says plot the following points on the grid above. Make sure you label them on the grid. Then state which quadrant or axis they're on. Okay. Hey, you know what? Try this on your own really fast. I'll freeze the screen up here. Let's see if we get the same answer. Give yourself about 60 seconds. I think 1, 2, 3, 4, 5, 6 points, about 10 seconds per point to state what quadrant or axis and plot them. Let's see if we get the same thing. That's what I ended up with. Couple of points hanging in midair, the 0.5s. Decimals, graphing decimals, Greg, isn't all that useful because, yeah, am I wrong?
In letter E, isn't that negative?
Oh, I'm sorry, it's not negative 2.5, it's positive 2.5, Mr. Dewick. Good gosh, got one wrong there, thank you. It's negative 0.5, positive 2.5, Mr. Dewick. It's going to hang in midair, right in the middle there, yeah? Is that right? And that makes it in quadrant dos, 2. Not bad. Graphing decimals is a bit tricky because you're kind of guesstimating. Technically, I might be a bit off. I might not quite be exactly halfway. Graphs are great for getting shapes and patterns. They're not that good for getting decimal values from a graph, but they're a good start. Oh, and quadrants, I got 2, the y-axis, quadrant 1, the x-axis, quadrant 2, and the y-axis. So now we're going to look at some real-life examples. To do this, the x and y axis are going to be given labels. They're going to mean something. Brianna, instead of just x and y, the y-axis is going to be time or length or something. When we look at a graph, we give the x and y values different names. We call the x values the domain, and we call the y values the range. Most kids have no trouble, Amy, remembering domain and range as words. They sometimes find it tricky to remember which one goes with X and which one goes with Y. It's alphabetical. D comes before R, X comes before Y. D goes with X, domain goes with X, range goes with Y. When you're drawing and interpreted graphs, there are 2 basic types. Qualitative. These are sketches with no actual numbers. All you're interested in, Sam, is the shape right? And then there's quantitative graphs with actual values. And you'll see what I mean by both in just a second. Do you need to know the difference between those 2 words? No. Will I use those 2 words in your homework? Yeah. I'm not going to ask you to define them on a test, though. So let's look at, turn the page or next page over. No, I went to a page. Let's look at a quantitative graph. Example 1. Says, look at the following graph of a salesman's travel from the office during the day. And what we're graphing on the, well, what are we graphing on the x-axis? What does it say? Look at the label. Time in hours. What are we graphing on the y-axis, Alex? How far away from the office? Okay. Lots of information contained there. A says, what quadrant is the graph located in? What quadrant is this located in? It's all positive values. Yes, quadrant 1. Why is it not located in quadrant 4, for example? We don't talk about negative time. Time moves forwards. I saw that Einstein said that. No, time moves forwards. And we generally don't talk about negative distances, although you may in Science 10 start to talk about a negative distance as being backwards. But since this says the distance from the office, you don't say I'm negative 10 kilometers from my office. Distances are positive. All right. When is this person at his office? How are you figuring that out? What are you looking on? What on this graph tells you that the person is in their office? Jordan.
The x-axis.
What about the x-axis? You're right, but I don't think I'm looking for math words. Yeah. So if I hear you right, if he's in his office, how high is the y value? 0 high? Are you saying it's the x-intercepts? Is that what you're saying, Jordan? Because you said x-axis, and I thought for a second he's going to say x-intercepts, and I'm going to be thrilled. It's the values on the x-axis. We gave those a name the other day. Did we not call them the x-intercepts? So when is the man at his office? It looks like from 8 to 8:30, yes? When else? From 12:30 to 1:30, I think. You know what? Let's use the metric time like them. So let's go from 12:30 to 13:30, because then it's easy for me to say, oh, it's exactly 1 hour, right? When else? Ooh, best guess? Now, we're going to assume 15:15 because we generally keep time in quarter-hour increments. If I say I'm going to meet you for dinner, I will never say, Alex, I'm going to meet you for coffee at 12:13. I'll meet you quarter after, half past, quarter to, right? So let's assume, I think it's valid to assume, what are you saying, 15:15? Until 1600. Now, you gonna make it? Yeah, okay. This graph has a bunch of x-intercepts. You see, look up. Don't write this down. That's an x-intercept, 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 that's an x-intercept. But there's a million in between there that I could also pick, yes? And so is that, so is that, so is that, so is that, so is that. So for us to list the x-intercepts by number would be tricky. I think if we wanted to list the x-intercepts, Brianna, our best bet would be to give the range of values that it occurs over like that. That's going to become important later on when we start talking about domain and range. You're going to find sometimes you can list them, sometimes all you can say is it's between these two numbers. How many hours total does the man drive in the day? First of all, on this graph, when is he driving? What are you looking for? What tells you that he's on the road? When there's a slope. So when it's level, that means he's sitting still. When there's a slope, and I can even do more than that. When the slope is uphill, he's heading away from work, yes? When the slope is downhill, what? Heading towards work. So I can get a lot of information from this. So how many hours does the man drive in the day? He drives this. How long is this right here? Okay, so let's just make a little list. 0.5 plus, how long is he driving right here? 0.5 plus, how long is he driving in this stretch? 1 plus, how long is he driving here? I don't think half an hour. What fraction of an hour is 15 minutes? 1/4. As a decimal? 0.25, yes. A lot of kids want to go like this, 0.15. No, 0.15 is not 15 minutes, right? 15 minutes is a quarter of an hour, it's 0.25. Sorry, it says what? What goes from 10 to 10:20? Sorry, which section are we talking about? This one here? It says he's driving from 10 to when? Yeah, that's that half an hour, right? We said this here is that half hour. This here is that half hour, yes? This here is that 1 hour, yes? It's this little tiny chunk right here, which goes from here to it's half a square, which I think is half of half an hour, quarter of an hour, 0.25. How long here? Also 0.25? Oh, and How long here? That's probably his commute home. That's a guess, but since the graph ends there, I might think that's him heading home. I don't know. Okay. I think I can do this without a calculator. What's 0.5 plus 0.5? Plus 1? Plus 0.25? 2.25? Plus 0.25? 2.5? Plus 0.5? Is it 3? He's on the road for 3 hours. How far away is the furthest store that the man travels to? That's the time. We want a distance. So we got to, now you're noticing, by the way, not only do you have to count the squares, you got to look at the scale. And so initially Darian said 65. No, he caught himself because he realized vertically each square is worth what? 10. This is a quantitative graph. It's got numbers on it. So 70 kilometers? Right here. Yoink. What's the next one? How many hours does the man stay at each store? Okay. Let's call this store A, store B, store C. How do I know that those are stores? Horizontal line means, Sam, time keeps moving. I thought Einstein said you can freeze time. No, time always keeps moving, but his distance isn't changing. Oh, that must mean he's staying in one place, yes? So how long does he stay at store A? How long does he stay at store B? Also 1 hour? How long does he stay at store C? Hour and a half? So you also got to be careful. Because each square is a half an hour, half of a square is half of a half an hour. What's half of half an hour? 50. Okay, so you got to read this a little carefully, right? So hour 15? Apparently that customer is a little more important, or had a bigger order, or something. What's the domain of this graph? That's all of the x values that appear. The domain, capital D. You with me? 8 to 8 I agree with. I don't think the graph quite stops at 16. 8 a.m. to 16:30 p.m. Now that's how we'd write it in English. You ready? Here's how we're going to write it in math speak. So write that down, because that's the less terrifying one. Sadly, the way we write it in math, Ty, it's great. It's short. It's a little scary. It's short, though. We say this. Domain. What's the smallest time value, the x-axis value that appears on this graph? Leave a space. What's the biggest x value that appears on this graph? It's all times between 8 and 16:30. So we're going to put a T in the middle. And what we want to show is that all the times are bigger than 8 a.m., because they are, but smaller than 16:30, than 4:30 p.m., because they are. How do I do that? That's bigger than 8 a.m. That's a greater than, what's a less than sign? T is bigger than 8. T is smaller than 16:30. If you're a little lost, don't freak out. We're going to spend a whole lesson looking at these. But right now, here's what I want you to notice. If I want to write in between two values, I actually put the variable in between the two values. Smaller one first, bigger one next, which kind of makes sense. And if you do that, smaller one first, bigger one next, it's always going to be a less than and a less than. That's how you say it's between those two. Now we have to add one more thing here. The fact that this graph includes 8 a.m. means I'm going to say or equal to. Have you guys seen that before from Math 9? No? Add that. And the fact that it touches 1630, I'm going to say or equal to. Don't freak out. Just write it down. Let's see if we can do the range. First of all, the range, if I just write it in less intimidating English, what's the smallest distance that appears? 0. What's the biggest distance? What's the furthest away he gets? Brody? 70? How would we write that in math speak? We would say the range is the smallest value is 0. The biggest value is 70. What variable did they put on the y-axis? Not the letter y. What did they use instead? That's the units. Distance. How about d for distance? To show it's in between those, what I want to show is that it's bigger than 0, which I can show by putting 0 less than d. And I want to show that d is less than 70. Then to show that this graph touches at 0, I put an or equal to. To show that it touches 70, I put an or equal to. Mr. Duick, I don't get... Relax. I'm going to do a full lesson explaining this, but what I'm trying to do right now, Simi, is plant a seed so that when I throw this at you on Wednesday, at least you'll be saying, oh, okay, I got some context. I hope. I says, calculate the speeds for each time the man is driving. Say, what? Well, how do you calculate speed? What's the speed limit on the low heat? No? Okay, you're getting your licenses soon. You need to know some of this. What's the speed limit on a city road? 50 what?
50 kilometers.
Kilometers is distance. That's not what the sign says. 50 what? Ty? I got to be fussy. It's not kilometers an hour. It's the word that I heard it.
Per hour.
Per. Okay, you ready? What's the speed?
50 kilometers per hour.
I don't care about the number. What are the units? Kilometers
Per hour.
per hour. Say it again.
Kilometers per hour.
Write that down on the margin over here. Is that how you write it? Yeah. Greg, do me a favor. Give her a little nudge. Yep. You okay? You back? You're tired. Back here, folks. What does that slash mathematically generally mean? Okay, division. Can you see that if I know how I measure speed, and this is why when you said kilometers, we say it that way, but it's kilometers per hour. It's kilometers divided by hours. You know what? It's the distance divided by the time. See how that's actually contained in the units? Yes? Cool. Let's do that. So for the first little journey before A, right there, how far does he travel distance-wise? You know what? I see, let's call this drive 1, drive 2, drive 3, drive 4, drive 5, and drive 6. I think we'll just do drive 1, 2, and 3. And if we get that, we're pretty good. So you ready? For drive 1, how far?
30 kilometers.
How much time?
Half an hour.
How fast? 30 divided by 0.5. By the way, 30 divided by 0.5 is the same as 30 divided by a half. Yes? Dividing by a half, same as timesing by 2. It's not 15. Right? Think about it. If you have one chocolate bar and we divide it in halves, How many pieces do we have? 2. If you have 4 chocolate bars and we divide each chocolate bar in halves, how many pieces do we have? 8. Dividing by half, same as timesing by 2. Now, if you're having a tough time, use your calculator on a test or a quiz. Don't be proud. But 60 kilometers an hour, is that a reasonable road speed? Yeah. Even though the speed limit is 50, most people do 60. Although on double lane roads, usually the speed limit is 60. The second journey. How far?
40 kilometers.
40?
Yes.
How much time? How fast? You know what? I know this person was probably on the low heat. Or on some kind of a highway that has a speed limit of 80. Or they were speeding, but probably not. It's tough to go 80 kilometers an hour in the city. There's red lights and things, yes? And let's do the third one. How far? By the way, before I do that, take a look at line A and line B. Sorry, line 1. Take a look at little slopey line 1 and slopey line 2. Which one was faster? 2. Which one looks steeper? 2. Are you saying that steeper on this graph means faster? Oh. Okay. Let's do 3. How much distance?
70 kilometers.
How much time? I can do that in my head. 70. Not sure what road he was on. There are some roads that have a speed limit of 70. Okay. Jay says, write a scenario, a story for the above graph. I think we've kind of talked about what might be going on. I think we've kind of been doing that as we've been discussing the question, yes? So let's turn the page. Example 2. Again, here is a quantitative graph because it actually has numbers and values. It says the following graph depicts the graphs of 2 cars racing. Car A has a 40-meter head start. It says label the lines as car A and car B. So this one here, car A or car B, and how can you figure that out? Oh, car A has a 40-meter head start, so that means its y-intercept would be 40, because at time 0, it's already got 40 meters going. Oh, this is another meaning for y-intercept. So you're saying this is car A and this is car B? I agree. B, what's the domain and range of car A? Let's do the domain first. Along the x-axis. So look at line A. What's the smallest x value it uses up? 0, yes? What's the biggest x value it uses up? 11. 11. So smallest is 0. Biggest is 11. My x variable is time. Times are bigger than 0 and smaller than 11. But it touches 0 and it touches 11. Relax. Let's see if we can get the range. What's the smallest y value that appears for graph A?
40.
What's the biggest y value that appears on graph A?
130.
Does it go up by 10? Yeah, it does. 130, leave a space. 130. The y variable is d for distance. It's bigger than 40. It's smaller than 130. It's between 40 and 130. And it does touch 40, and it does touch 130. Eventually, you'll look at some where it doesn't quite touch, say, the 130. It gets closer and closer and closer and closer and closer, but you can tell it's veering off. We'll have to deal with that differently. Try doing the domain and range of car B on your own. I won't freeze the screen. You can look up if you need to, but see if you can figure it out yourself. Car B. I did that. The time values that are used up are between 0 and 8 seconds, and every single value is used up. The distance values that are used up are between 0 and 130, and you do touch at 0 and 130. D says, who won the race, and how do you know? Who won the race?
B.
Greg. B? Convince me.
They went the distance in very less time.
Exactly how much time? Ah. B. Finished in 8 seconds. Ooh, E. At what time did the faster car overtake the slower car? What are you looking for on the graph? Ooh, you even used a math word. What did you say? When they what? Intersect. Oh, I thought he was going to say when they cross, dude. When they, yeah, the intersection point. That actually is going to become important enough that later on in this course, we're going to spend an entire unit learning how to find where lines cross without bothering to graph them. Because graph paper is a pain. If you don't have it, now what? And this might give you an idea of why that might be useful. If you had the equations for both of these cars, it would tell you when the first car caught up to the second car. Sorry, when? What time? 5 seconds. T equals 5 seconds. Oh, at what distance on the track did the faster car overtake the slower car? 80 meters. G says, give the speeds of each car in meters per second. So you can measure speeds in kilometers per hour, which is what you do on roads. In physics, in science, and those of you that are in Science 10, you'll probably shortly be starting your motion unit. We generally measure speed in meters per second. That's the preferred physics way. So meters per second, that actually tells you how to calculate it. Meters/second says distance divided by time. So let's do car A. How far does car A travel grand total? Don't say 130 because it doesn't. Ah. 90 divided by how long does it take to travel 90 meters? 11? Is that right? This one doesn't work out evenly. What's its speed? Okay, calculator time now. Unless you know how to do 90 divided by 11 in your head. 8 point. It's going to be a 2. 8.1, and there's going to be 9. Is it 8.1818181818181818?
Yes.
Apparently someone here can Divide by 11 in his head. 8.18 repeating meters per second. Car B. How far?
130 meters.
How long? 8? 130 divided by 8 is going to be 65, divided by 4 is going to be 32.5, divided by 2 is going to be 16.25. Double check me. Is it 16.25?
Yep.
Thank you. You've got a good audience. Try the veal. Tip your waitress. In fact, car B is going almost, but not quite, twice as fast as car A. Right? So those are quantitative graphs. You can get lots of data. Qualitative graphs, we don't include numbers. We just want the correct shape. As an example, the following depicts the distance of a child's head above the ground when they are on a swing. Did I put any numbers on there? No. But can you tell kind of what's going on? I hope so. Why doesn't the graph touch the bottom? You've been on a swing, yes? Do your heads hit the ground when you're on the swing? Not unless something's gone horribly wrong. That might explain. Oh, sorry. So why does the graph not touch the bottom? When you're on a swing, your head doesn't. Come on, T. Come on. Hit the ground. Now, why doesn't the graph go back and forth like a real swing? Well, now you have to think a little bit. You see, what's happening is time moves forwards. When you're on a swing, you're at your highest, then you come back down, then you swing up again, then you come back down again, then you swing up again, then you come back down again, then you swing up again. But time keeps moving forwards. In fact, this particular graph here is so important in Math 12, you'll spend an entire unit looking at this. These are called sinusoidal or trig functions. Hugely important. Anything that swings or oscillates is a trig function, and lots of things in physics swing and or oscillate. What quadrant are we in? You know how I know? Because when I swing up and time moves forwards. Right? So B, I gave you the answer. We didn't write it down because it's a long answer, but hopefully you understand. Turn the page. Put your pencils down. Look up. Close. Here's the deal. I'm going to give you several graphs. You need to pick which you think is the graph that best describes this particular situation, and you're going to have to vote. I'm positive. How high you hold your hand up is how sure you are of the answer. I'm positive. I'm pretty sure. I'm only voting because Mr. Duke will make fun of me if I don't vote. Okay? So here's the first one. It says, circle the graph that best describes the given statement. You know what? I'm going to go like this, and I'm going to send it to OneNote so I can write on this. And we're going to go right to here. Identifying graphs. Okay, so here's our first one. A train pulls into a station and lets off its passengers. And the four graphs, can I fit all four in there? Not at that magnification. I can't at that magnification. Here's the four graphs. On the y-axis, we have speed. On the x-axis, we have time elapsed. So there are the four possible graphs that describe a train pulling into a station and letting off its passengers. And you need to ask yourself, which of those do you think is the best example of what that graph might look like? Now, these are qualitative graphs, no numbers. Who thinks graph A is correct? Raise your hand, nice and high. Who says graph B is the right one? Raise your hand, nice and high.
They're all A though.
Sorry, the second graph. Who says the second graph? 1, 2, 3, 4, 5, 6, 7, 8, 9. Who says graph C? None. Who says graph D, the fourth one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Only 19 people. 6 of you are wimps. I'll get you next time. So here's the rule. You can either defend your own answer as being right, or you can attack someone else's answer as being wrong. You can attack or defend. Convince me that you're right or that someone else is wrong. Someone give me an argument. Those of you that picked the second graph, tell me why. Or those of you that picked the fourth graph, tell me why. Ben.
Because with the second graph, it's going down a slant, implying that as time's going by, as it's pointing to the station, it's slowing down.
Okay, so when a train pulls into a station, does it slow down?
Yes.
So if it didn't slow down, I think you'd have a horizontal line. I think that can't be right because that train is not slowing down at all. Right? What's happening right there? What's happening right here? Oh, it's come to a stop. So this one here, the train speeds up, slows down, speeds up, slows down, and I guess you got to jump for it. Right? It is not coming to a stop. Now, this one does come to a stop. What's wrong with this one? Yeah. Well, this is coming to a very, very rapid stop. By the way, this is a graph of a head-on collision, and this is why you die most often in head-on collisions. Those of you that take any physics next year will actually look at this kind of a thing. This is traveling at a steady speed, steady speed, steady speed, steady speed, and in like 1/1,000,000th of a second, you come to a stop. That's a crash. That's hard on your body. We don't want to kill our passengers. I think the answer is the graph number 2. Second one, a man takes a ride on a Ferris wheel. And we're graphing distance from the ground versus time elapsed. How high you are from the ground versus time elapsed. Which of those do you think is a better graph? Who says A? 0. Okay. Who says B? Second graph. 1. Oh, and now people looking around. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then Greg looked around and joined in. 12. Grab some conviction, Greg. Who says the third graph? 0. Who says the fourth graph? 1, 2, 3, 4. Okay, I'm going to keep track of who's not voting next time, and I'm on you. You better vote next time. Because only 16 of you voted. All right, attack or defend? Convince me you're right or that someone else is wrong. Alex.
I'm sure like the second graph, but on the fourth one, you don't go backwards in time.
Oh, so your argument here is we're moving forwards in time, we're moving forwards in time, and now we're moving backwards. I have another issue with this, by the way. Apparently, at the same time, this person is that high, and that high. Unless something's gone horribly wrong, I don't think you can be at more than one height at the same time. By the way, which of those graphs looks the most like a Ferris wheel? Graph number 4. Which of those is, but it's not, right? So don't just look at the shape of the graph and think, oh, it looks like the ride, it must be right. Think through what's going on there. So I don't think this one is good. In fact, my same issue with this one, I think, oh, by the way, does this graph here, graph number 4, pass the vertical line test? It's not a function. That also tells you it can't exist in real life. Oh, some of this is useful. Does this graph pass the vertical line test?
No.
Ah. So second or third one? Which one and why? Ben, what's going on? Okay, so right here, what's going on?
You're going at sort of like an even, sort of like.
How high are you right now?
You're at 0 right now.
You're getting on the ride. In fact, I think you're walking up onto a platform, and I can even tell you how high the platform is. It is, I think, about that high. Yes? You get on, roller coaster goes up, roller coaster goes down, roller coaster goes up, roller coaster goes down. In fact, the graph of a roller coaster is very similar in shape to the graph of what you feel like when you're on a swing set. Your height changes up and down, up and down. Okay? Didn't ask you, or didn't care about where you were left, right. It only asked about how high you were. So, third one. A woman climbs a hill at a steady pace and then starts to run down one side. And we are graphing time on the x-axis and speed on the y-axis. A woman climbs a hill at a steady pace and then starts to run down one side. We're graphing speed versus time. Who says graph A? 1, 2, 3, 4. Who says graph B, the second one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Who says the third graph? Who says the fourth graph? Who didn't vote? You did?
Yeah, I voted for the second one.
You did?
Yeah.
Ooh, okay. Attack or defend? Alex.
For the first one, it says he stays steady, so that's why there's a straight line.
Oh, because we're graphing speed, so you're saying that a steady pace, if you're graphing speed versus time, wouldn't change its height?
And then you,
So you're saying that that gets rid of that one? Oh, that gets rid of that one. Oh, that gets rid of that one. Keep going.
and then you gain speed running down one side of that.
So your speed gets higher? I agree. By the way, which one looks the most like a hill? The second graph. Don't let the shape of what we're talking about fool you. Ask yourself, what's on the y-axis, what's on the x-axis, and how do they change? Child swings, oh, we already did this one, right? Turned out to be that one there. Child climbs up a slide and then slides down. Child climbs up the ladder of a slide and then slides down. Now, hopefully by now, most of you have been burned enough that you're skeptical of graph 2, even though it looks just like a slide. Think very carefully before you choose that one. Don't fall into that trap, unless maybe it is. You ready? Oh, and we're graphing speed versus time. So not height versus time, speed versus time. Graph 1. Oh, 0 should go there. Graph 2. 1. You know what? That was kind of a... So we'll go a half. Graph 3. 1, 2, 3, 4, 5. Graph 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Attack or defend? Yep.
Thing is, with number 4, it's measured by speed. So as you're going down the slide, you're supposed to be going faster, not slower.
Oh, I've been on slides. When I go down a slide, my speed increases?
Yes.
And what's this saying when I'm on the slide? This one is saying somehow that my speed is what?
Increasing.
That's decreasing? Sorry? Oh, that also gets rid of that one and that one? Okay, what the heck is going on here then in this graph? Let's see if we can set up the scenario. There is a constant, a horizontal line, which means a steady speed. What's that?
Walking up the slide.
In fact, I think that's walking up to the slide. Then the speed decreases. What's that? Climbing the ladder. It hits 0 here. Well, it should hit 0 there for a split second. Why? That's a long ways down. You got to work up your nerve. You sit down and you're... Right? What's this?
Going down the slide.
Going down the slide. What's this rapid decrease in speed? Hitting the ground. Okay. Back to our notes. Pick up your pencils. Do you see what I mean with a qualitative graph? You can get some stuff. So Chloe climbs the stairs to a slide, stops at the top, and then slides down. Which best represents the scenario? Now we're graphing height versus time, not speed versus time. Which one? Well, I don't think this is going to help. The latter part is the same for all of them. So what happens to your height when you go down the slide? It gets smaller. Oh, all of these get smaller. What happens to how fast it gets smaller? Do you speed up? Then I think I'm looking for a graph that initially barely starts to change its height, but then changes its height faster and faster and faster. And I think it's that one, isn't it? Kira got that one right? Oh. Example 5. I think this is it. Yes, good. Draw a graph that is a reasonable representation of... Oh, sorry, I skipped example 5. Sabrina rides up and down a steep hill on your bike. Which graph best represents speed versus time? Go ahead. 2, convince me.
Because when she's riding up, she goes slower going up.
So you're saying that she's speeding up as she's going up the hill, and then she's slowing down when she goes down the hill?
No.
I think graph 2 looks like a hill. Huh? Graph 1, I think. She's pedaling and she's taking a run at it. Yes? She hits the hill. What happens to her speed? Down, 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 down. She makes it to the top, nearly comes to a stop. Not quite. And then what? Speeds up. Yeah, I think it's graph number 1. Are we learning not to necessarily pick the thing that looks like it? Yeah. Okay. I'll get you the homework in a little bit. Or check online. It's going to be some of the questions from here, and I have a sheet for you too. Give me 1 second. Let's see if we can sketch some. Draw a graph that is a reasonable representation. A ball is thrown upwards. It bounces 3 times before coming to a rest. Okay. So, I'm going to throw it. At time 0, is the ball on the ground right now? How high? You know what? Let's eyeball it. Let's say, Brody, about that high. It's a qualitative graph. No numbers. I know it's not on the ground. Throw it up. Woo! Oi! Right? Gets to the top, what happens? All the way down? Bounce once. Bounce twice. And it comes to a rest on the 3rd bounce for some strange reason. I'm not quite sure if those are right. I'd have to think about it for a while, but I'm close. Second one. A pot of water is heated to boiling on a stove and then left to come back to room temperature. And we're graphing temperature versus time. Okay, when we start out, how hot is the water? 0 degrees? Really?
Room temperature.
So if it was 0 degrees, it'd be ice. Am I starting out with ice? See, I don't think this graph is going to start right. I don't think it's going to start right there. Room temperature, I heard somebody say, or sink temperature. Does your water come out of the sink? Well, you know what? Let's go room temperature because you can control how hot and cold. So let's put room temperature, I don't know, right about there. Now we're going to heat it. What's going to happen? How about boiling is right there? We'll let it boil for a while. Then we turn off the stove. Now, the question, and I have to think about this, is does it cool off faster than it heated up or not? Probably it cools off slower than it heated up. Well,
It's cooling down at room temperature.
in fact, here's what I think really happens. It cools off really fast at first, and then it cools off slower and slower and slower, but eventually hits room temperature. I think something like that is really what happens. Because I notice when something's boiling and I flip the stove off, if I remove it from if you ever lift a boiling pot from the stove, it stops boiling within about a second and a half when you hold it in the air there. Right? Those of you that have cooked. I think something like that. Ah! A little preachy, but still this works. Your health over your lifetime if you smoke. Well, you're born fairly healthy. And let's assume you don't start smoking when you're 5. Let's assume, can you put it please in the proper block? Pretty good, pretty good. Start smoking cigarettes right here. What do all the studies say happens to your health? Right? Something like that. Last one. A skateboarder starts at the top of the hill, accelerates, and then smashes into a car. Okay? At time 0, at the top of the hill, how fast are they traveling? Okay, so I think we can assume reasonably well that this graph goes through 0, 0. They accelerate. What's going to happen to their speed? Let's say they get to the bottom of the hill and they coast straight for a little while, so probably level off. How would I show them hitting a car? No, okay, we won't do that either. Okay. What's your homework? A few things. You can try number 1. Three. 4B, 4C, 5, I think we can do 6 as well. So there are answers attached. Then I have one more thing for you. Little sheet. So, first one says, what kind of monkey can fly? Sketch 2 graphs for the situations. Match each graph to one of the answer choices. And write the letter of your choice. So, Erica walked from home to a friend's house, watched time for a while, and then walked back home. In your 2 quick sketches, and you can do them, I think, on here if you sketch small, or you can do it on a separate piece of paper. In the first graph, you're going to let the y-axis be the distance from home, or you can simply ask which of these would be the correct graph if you were graphing distance versus time. In the second graph, speed versus time. So, does that make sense? Yeah? Okay. Oh, and then write the letter of your choice in each box containing the exercise number. So if you think, for example, the answer to number 1 is graph D, you'll put a D in the number 1 right there. There's a couple of challenges on the back page. Sketch a graph using the situation for the situation using the variables given. Can't even read. Match your graph to one of the answer choices, and then write the letters. So number 1, Roy rode his bike up a hill at a slow but steady speed, then went faster and faster as he rode down the other side. Time on the x-axis, distance traveled on the y-axis. So this is not speed, this is distance versus time. See if you can figure out which one's which. These are tricky. See how it goes.